Hi, so I'm here with another video on capacitors, and in this class we are going to discuss about capacitor connected in an external cell with an external cell, combination of capacitors, and the effect of dielectric when it is partially inserted between the plates of a capacitor. Shall we see the first part? Consider a capacitor, an uncharged capacitor connected to a cell. Uncharged capacitor connected to a cell by means of a switch. Initially, the switch is open, as you can see. What is the initial charge on the system? Initial charge on the system. Is there any charge on this plate? If I call it as A and B, what is the charge on plate A? 0. What is the charge on plate B? That also 0, which means initial charge on the system is 0. In the second figure, I'm going to consider that the cell is connected and the switch is closed. The same capacitor, the plate is A, this plate is B. Now the switch is closed, that means a connection is restored here. What happens as a result of that? I'm sorry, this is a cell. Okay, so let the supply voltage be V. Now cell is connected. The terminals are connected by, the switch is closed. As I told you in the previous video, a capacitor is an arrangement that consists of two conducting plates. And what differentiates a conductor from insulators and semiconductors? The number of free charge carriers. Number of free charge carriers differentiates a conductor from insulators and semiconductors. So this conductor contains enormous number of charge carriers. Now the plate A is connected to the positive terminal of the battery. Plate A is connected to the positive terminal of the battery. Plate A connected to the positive terminal of the battery. So what will happen? Electrons on this conductor will what happens? They will tend to align on the outer edge and positive charges inside. Okay, with your permission, I am drawing it slightly bigger. Negative charges here, positive charges here. As a result of positive charge on the inner surface of plate A, what will happen? Induction. And the process of induction, negative charges will be induced here. So, positive charges here. Yes. Now the question I am asking you is, will these negative charges remain here? Answer is no. Why? Because this positive polarity will attract these negative charges. Negative charges will flow to ground. Negative charges will flow to ground. And similarly, what will happen to this positive charge? That positive charge also will go to ground. During the flow of negative charges, a current will be set up here. And during the flow of positive charges here, a current will be set up here. During the flow, that is what I am saying. I use the sentence, during the flow of these negative charges and positive charges, a current is here. Now, which means this plate has got a charge Q. Then what will be the charge on the negative plate? As I said, this is plate A and plate B. Now, plate A is charged Q. What is the charge on plate B? Yeah, it's very simple. Because this plus Q means this should be minus Q. Which means what is the final charge on the system after the plates are charged? Charge on plate A is plus Q. Charge on plate B is minus Q. Which means final charge on the system is also equal to 0. Initial charge on the system was 0. Final charge on the system is 0. Which means the charge is conserved. Now, what is the magnitude of Q? Magnitude of Q, At a steady state, steady state means that condition when the plates of the capacitor is fully charged. Steady state is that condition when the plates of capacitor is fully charged. Think, it is just like we are eating. There will be a stage when we cannot eat any further, right? Why? What is the reason? Pet to bhar gaya. That means stomach is full. Can you charge any further? Any further charging is possible? Answer is no. So steady state is that condition when the plates of the capacitor is fully charged. Fully charged. When the plates of the capacitor is fully charged, that condition is called steady state. So under steady state, once it is fully charged, no more negative charges can come down. No more positive charges. As I said, positive charges are coming down. Don't be confused. Don't be against me. Positive charges are moving means negative charges are going to that direction. Okay, it is not wrong to say positive charges moving. When we use the convention, the motion of the positive charges, it does mean that the negative charges are moving against them. When positive charges are moving down, if I say, that just means that the negative charges are moving against that one. Okay, so at steady state is that condition of the capacitor when it is fully charged. That state of the capacitor when it is fully charged, when the plates are fully charged. So initial charge on system is 0, final charge on system is also 0. That means a capacitor obeys charge conservation, right? Capacitor obeys charge conservation. I also use this idea to say one more thing, that everyone tend to say that a cell is a source of charge. And I will tell you, a cell is not a source of charge, but it is a source of energy. What does cell do in the process? This plate is positively charged, this plate is negatively charged, I can say. In the process, what a cell is doing is, it is supplying energy. A cell is delivering energy to the capacitor. Regarding energy, we will study it later. So this is an idea you need to understand when you study about a capacitor. Now in the next discussion, what we are going to do is, we are going to consider the series combination of capacitors. Series combination. I think my pen is just gone. Series combination. Okay, what do you mean by the term? What do you mean by series combination of capacitors? Series. I think you have studied in 10th class about series combination of resistors. In +1 you have studied series combination of rods, series combination of springs. What do you mean by series combination? In series combination, it is one after the other. That means what is series combination of capacitors? Okay, take it. This is capacitor 1, it's series C1, C2, C3. This is connected to a supply voltage. This is what I am saying as series combination. Yes. Now, what is same in series combination? Let us understand this. So as a result of connecting to this, okay, let me make it slightly bigger for our proper understanding. This is capacitor 1, this is capacitor 2, this is capacitor 3. C1, C2, C3. Okay, let us assume that the inner surface of this one has got a charge plus Q. Then what will be the charge on the inner surface of this one? The other, what I am saying is the other negative charges have gone to the cell. Okay, so this will be minus Q. As a result, positive charges will be accumulated here and that will be plus Q. But this is a conductor, no. And as a result of accumulating positive Q here, this positive Q what is occurred here will shift to this plate and it will be plus Q here. As a result of this, plus Q minus Q will be induced here. Again this will be plus Q. Again here will be minus Q. Again here will be plus Q. But what happened to that plus Q? What happened to that plus Q? That plus Q plus Q plus Q plus Q will go to the negative terminal of the battery. Right? That plus Q will go to the negative terminal of the battery. I repeat. Now as it is connected, this is the positive terminal of the battery, cell. As a result of that, the inner surface, we have seen just previously, the inner plate of this will be positively charged. Due to induction, negative Q will be induced here, positive Q here. As a result, as it is connected by means of a conductor, the positive charge, which is an unbound charge here. Unbound, why? Because this positive and this negative are bound. Upon this, the positive charge here comes out to be an unbound charge. That positive unbound charge will be flowing to the next plate. Then negative Q will be accumulated here. Positive Q again here, negative Q here. What are the positive charge coming here? That will flow to the ground. Right? Okay, so that means what is same? You can see on each capacitor, the charge on this plate is plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. So my question, what is same in series combination of a capacitor? In series combination of capacitor, it's very important to understand the combination. So in series combination, the most important thing you can understand is that the charge on the capacitor is same. Charge on the capacitor is same in series combination. In series combination, what is same is charge on the capacitor. Now, the supply voltage is V. Let us consider the voltage across this one is V1. The voltage across this one is V2. The voltage across this one is V3. Why V1, V2, V3 are different? Because capacitance are different. Right? Because you can say V1 is equal to Q divided by C1. Q means charge on each capacitor. We have seen in previous video. V2 is equal to Q divided by C2. V3 is equal to Q divided by C3. Can I conclude that V1 is equal to V2 is equal to V3? Can I conclude that V1 is equal to V2 is equal to V3? Can I conclude that V1 is equal to V2 is equal to V3? The answer is no. I cannot. Why? Because the C1, C2, C3 are different. C1 is different from C2, C2 is different from C3, so that means V1, V2, V3 are different. But what is V? Potential. What is potential? Means energy of 1 coulomb charge. Potential means potential energy of 1 coulomb charge, which means I can say potential will be different in the case of series combination. Now what I can say is that from the conservation of energy, V is equal to V1 plus V2 plus V3. As I used only 3 capacitors, so I can say V is equal to V1 plus V2 plus V3. But what is V? I can say V is equal to Q divided by C effective. What I am doing is that I am replacing the combination with a single capacitor which contains a charge Q. The combination means that Q divided by C effective is equal to, what is V1? Q by C1 plus Q divided by C2 plus Q divided by C3, which implies 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is the effective capacitance of the combination of capacitors connected in series. 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is the answer when you connect 3 capacitors in series. Now we are going to generalize the answer if n capacitors are connected in series. N capacitors are connected in series, then what is the answer? 1 by C effective is equal to, you can say the answer easily, 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. plus 1 by Cn. The effective capacitance satisfies the condition 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. plus 1 by Cn. When you see this equation, you are thinking about something else that you learned in 10th class. That is regarding the resistors in series, don't you? Now you will say, sir, when you connect resistors in n resistors in parallel, then your answer is 1 by R effective is equal to 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. plus 1 by Rn. Yeah, the same result I am getting. Resistors in series, resistors in parallel, capacitor in series. Both use the same logic. Springs in series, capacitor in series, which follow the same result. As now I will say, if capacitors are identical, means what? C1 is equal to C2 is equal to C3 is equal to etc. is equal to Cn is equal to Z. That's where I say if the capacitors are identical, then what will be 1 by C effective is equal to 1 by C plus 1 by C plus etc. plus 1 by C. That it means 1 by, when you take 2, 1 by C plus 1 by C is 2, plus 1 by C is 3 by C, plus 1 by C is 4 by C. If you have n times that, then this is going to be n by C, or I can say C effective is equal to C divided by n, and that is your answer to the problem. C effective is equal to C by n. When n identical capacitors are connected in series, the answer is C effective is equal to C by n. I hope the part is clear to you. If it is clear, let us move on to the next condition, that is parallel combination. Now it is very simple. In series combination, what is same? Charge on the capacitor is same and potential is different. Now let us consider the parallel combination of capacitors. Shall I? Okay, take it. If capacitors are connected in parallel, okay, just like we did earlier, I will take 3 capacitors. This is 1, this is 2, this is 3. Connected to a supply voltage V. Okay, let me take this point as A and this point is B. According to the electrostatics of conductors, you have learned that every point of the conductor is at the same potential. So if I say the potential of this point is VA, what is the potential of this point? VA, which means the points with the same potential I am going to label with the same letter. This point is A, its potential is VA. This point has a potential VA, that means this point is also A. This point, what about this point? Again same conductor. Same conductor means potentially same. What is the potential of this point? Again A. Again, what is the potential of this point? A. Potential of this point? A. Oh, sorry, VA. That means A itself. What potential of this point? VA or A. This point is A. That means that all the points which I marked here, the potential is VA. The potential of all that points is VA. Ready? Now this point is B. Tell me what about this point? Joined by the same conductor. B. What about this point? Joined by the same conductor. B. No resistor, neither capacitor, nothing here. What about this point? B. 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 Now you can see what? One plate of each capacitor is connected to the terminal A. One plate of each capacitor is connected to the terminal A. Other plate of each capacitor is connected to the terminal B, which means potential difference across each capacitor is VA minus VB. I repeat, one plate of each capacitor is connected to the terminal A. The other plate of each capacitor is connected to the terminal B. One plate of each capacitor is connected to the terminal A, that is to the same potential. The other plate is connected to the same to the terminal B. Such a combination is what is called a parallel combination, and you can see that the potential difference potential of this capacitor, that is the potential difference between the plates, is VA minus VB. The potential difference of this one is VA minus VB. Potential difference of this one is VA minus VB. That means all three capacitors have the same potential difference. That means how to identify a parallel combination. I can say in parallel combination the potential difference is same. If the charge flowing from here is say Q, what will happen to the charge coming here? The charge here will be Q1, charge here will be Q2, charge here will be Q3. That means in parallel combination potential difference is same but charge is different. Now recall what we studied in series combination. In series combination charge is same but potential difference is different. In series combination we conserve the potential, whereas in parallel combination, so this charge Q is reaching here, I can write Q is equal to Q1, total charge Q is equal to Q1 plus Q2 plus Q3, right? From the conservation of charge, what is entering here is Q, what is leaving is Q1, Q2, Q3, that means Q is equal to Q1 plus Q2 plus Q3. But what is Q1? Let me call these capacitors by name C1, C2, C3. Q1 is equal to, as we know, it is C1 into V, right? Because VA minus VB is equal to V, right? Q1 is equal to C1V. Now tell me what is Q2? C2V. What is Q3? C3V. That means total charge Q is equal to, tell me, C1V plus C2V plus C3V. Potential difference same. Now left side of the thing, I will write as C effective into V. So from here, both sides V will be cancelled, otherwise, and I can say C effective is equal to, tell me, C1, C2, C3. This is the answer. When capacitors are connected in parallel, resistors connected in, you find the answer. Effective capacitance of capacitors connected in parallel, C effective is equal to C1 plus C2 plus C3. Now we will generalize this by considering N capacitors. What will be C effective is equal to C1 plus C2 plus etc. plus Ck. If the capacitors are identical, that means C1 is equal to C2 is equal to C3 is equal to etc. is equal to Cn is equal to Z, means what is going to be C effective is equal to C plus 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 C plus. It's going to be NC. The effective capacitance when identical capacitors are connected in parallel is C effective is equal to NC. So I tell you to study this much portion for today. In tomorrow's class, I am going to discuss about the combination of dielectrics. Study well. Thank you.